Thank you, Alex. Good afternoon. My name is Eric Fossum, and this is the first Jones seminar that I've ever hosted, so it's a first for me. And nevertheless, I am very pleased to have John Callas here from JPL. John and I were former colleagues at JPL about a million years ago. And since that time, John has moved upward at JPL to the point where he's now the project manager, and has been actually for a while, of NASA's Mars Exploration Rover project. John is a Massachusetts Yankee. He grew up near Boston. He received his bachelor's degree in engineering from Tufts in 1981, and then he went south from there to Brown University, where he got his master's and PhD in physics. He then in 1987 joined JPL to work on advanced spacecraft propulsion. And I didn't know we still did propulsion at JPL. Yeah, it's a small part. But anyway, in 1989 he began working supporting the exploration of Mars with the Mars Observer mission, and has since worked on 7 Mars missions. John's also involved in the development of instrumentation for astrophysics and planetary science, and in his spare time he teaches mathematics at Pasadena City College as an adjunct faculty member. So let's please welcome Dr. John Callas.
Thank you, Eric. Good afternoon, everyone. It's a pleasure to be here. If you're wondering about those Massachusetts people, we're the ones that drive over the border to buy our liquor and shop at the malls just north of the border between Massachusetts to save on all those sales tax. Anyways, I want to share with you an adventure that was originally only supposed to last 3 months and is still ongoing after 8 years. It is still amazingly productive, and there's still a lot of excitement ahead. So let me begin with this object. This is the planet Mars. Mars was one of the planets known to the ancients, so for hundreds of years human beings have been fascinated by this world. It's been the subject of lore, of mythology, and of great scientific study. If you are a science fiction fan, you know that Mars is featured by James Joyce Burroughs and others. And of course, H.G. Wells wrote War of the Worlds over 100 years ago. And you had the Orson Welles radio broadcast back in the 30s about invasions from Mars. And when you go to the supermarket, the tabloids always have the space aliens coming from Mars. So it has been very much in our culture. And part of that is for 2 reasons. One, that Mars has many similarities to the Earth, and it also has many differences. For example, Mars has a polar cap. It has 2 polar caps, very much like the Earth. It's tilted on its axis by 25 degrees, very close to the Earth's 23 degrees. So it has 4 distinct seasons. And this led astronomers like Percival Lowell over 100 years ago in Flagstaff to study the planet and see these albedo features change with time. He postulated that these were crops or other foliage that were changing with the seasons. He went further to say that there was an advanced civilization on the planet that were building canals to bring life-giving water from the polar caps down to the parched equatorial regions. And the mythology about Mars extended all the way into the dawn of the space program. And it wasn't until the space program, with the launch of Mariner 2 in 1964 that arrived at Mars in 1965, and then subsequently with other missions, that we got our first close-up look at the planet. This is an image taken by one of the Viking orbiters that were launched in the mid-1970s. And you can see here that Mars has features that look familiar to us, like the craters on the moon, although we see that these craters have been eroded away and worn away, so they're not as sharp and as distinct as the moon. So clearly there's been some process at work on the planet. We see that there's a thin, tenuous atmosphere. Mars has a carbon dioxide atmosphere. It's only about 1% as thick as the Earth's atmosphere, so it's very tenuous. But we don't see any shopping malls, any shorelines, any highway systems on Mars. And the Viking missions were focused on the search for life. So there were 2 orbiters and there were 2 landers. And here's a photograph from one of the Viking landers that touched down. It had a robotic arm that would reach out and take soil from the surface and introduce it into 3 different experiments. and there were 3 parallel controlled experiments. So Viking was very much focused on whether there was life on Mars, because you have a carbon dioxide atmosphere. There was evidence, some tantalizing evidence that there might be some water on Mars, or water at some time, so we were looking for things that might grow. Well, Viking found no conclusive evidence that there was any life on the planet, and that pretty much closed the door on exploration of the planet for about 2 decades. And it wasn't until the mid-1990s that interest was renewed in the exploration of Mars. And one of the pieces of news that excited that interest was this rock here. This is the Allen Hills meteorite. It is a Mars meteorite that was found in the Allen Hills region of Antarctica. And by studying the entrapped gases in the rock and identifying the isotopic ratios, it matches to the isotopic composition of the atmosphere on Mars. So we know this is a rock from Mars as opposed to a rock from the Earth or a rock from the Moon or Venus or the asteroids. So it is a messenger from the planet Mars. And scientists examined under microscopic analysis the inside of this rock, and they found features, I call them features, that look like they might be fossilized life. They found differentiated chemistry that might be indicative of metabolic processes that might have happened a long, long time ago. It's very controversial. Very few scientists accept that this might indicate there was life on Mars, but it did create a lot of interest. And around that time, on January 4th, 1996, we touched down on the surface of Mars with a Mars Pathfinder mission. Now, Mars Pathfinder was an engineering mission. Its purpose was to test out various new innovative technologies to land on the surface of Mars. One was the use of airbags to touch down. But it also carried a very small and adorable little rover called Sojourner. Sojourner was about the size of a microwave oven. It's 6-wheel drive, solar powered, and radio controlled. The radio signals it gets from the lander. And by the way, if you're wondering who's taking the pictures, there is a camera on the lander taking pictures of the rover. And what Pathfinder demonstrated to us was that freely roving robotic vehicles are an excellent way in which to conduct science in an alien world. But we were frustrated by this mission in that the rover was virtually tethered to the lander, so it couldn't go more than about 10 or 12 meters from the landing site because of the radio link that it was required. And so we were frustrated by wondering, well, what is this thing up here? We called this the couch. And what's just over the ridge? What's on the other side? And so we'd love to be able to go and explore freely on the surface of Mars. I mean, the frustration here was like going to Disneyland, but you're not allowed to go on any of the rides. That wasn't very satisfying. But at the same time Pathfinder was landing on the surface of Mars, there was another spacecraft going into orbit around Mars, and that was called Mars Global Surveyor. And as Global Surveyor, as its name implies, it was intended to do a broad survey of the planet. In a sense, we kind of got burned scientifically with Viking, that we focused that very expensive mission on a narrow set of objectives, the search for life. So Global Surveyor was meant to do, okay, let's step back a moment and do a global perspective of the planet. And this is some of the altimetry data from the laser altimeter that was carried on the spacecraft. And so from this, color corresponds to altitude. So white and red are high elevation, blue and purple are low elevation. And what's striking about this is you see that the northern hemisphere of Mars is not only very low, it's also very smooth. And then you can see features that look like flow channels. And this has led some scientists to postulate that maybe at one time Mars had a great northern ocean, and these were the tributaries that fed that ocean. In fact, this surface is so smooth, it's one of the smoothest surfaces found in the solar system. The only other surface in the solar system that is as smooth as that is the bottom of the ocean here on the Earth. So this was compelling, and it was exciting. Global Surveyor also carried a high-resolution camera. This is an image from that camera to give you a sense of the scale. This is about 3 kilometers, or about 2 miles across the field of view here. And this is a canyon system on Mars, carved by water. But what's interesting is the narrow channel down the middle of this canyon system. This means that this canyon was carved by slowly flowing water. So this didn't form overnight. This didn't form over the period of weeks or months. This meant that there was water, liquid water, persistent on the surface of Mars for thousands, tens of thousands, perhaps even millions of years. If you remember your phase diagram from water from high school chemistry, do you? That below a certain atmospheric pressure, water is no longer a liquid. It's either an ice or a vapor. And that's at about 6 to 8 millibars of atmospheric pressure. That's currently the atmospheric pressure on Mars. So liquid water can't exist on Mars today. So the fact that we see evidence of not only liquid water, but sustained liquid water on the planet means that there had to have been a thicker atmosphere at Mars at one time. So more and more questions are emerging. Was there liquid water? How long was it there? When was it there? What happened to it? Was there a thicker atmosphere? What happened to that atmosphere? And was there an environment that was habitable to support life? So to answer these kind of questions, the best way is to go back down to the surface of Mars with a much more capable roving vehicle, and that's the Mars Exploration Rover's Spirit and Opportunity. That's my mission. And here's a photograph of one of the rovers in development at JPL in Pasadena. And of course, these are normal-sized people, so you can get an idea of the size of the rover. It's about the size of a riding lawn tractor. It's 6-wheel drive, so each of the 6 wheels are independently driven. The 2 front wheels and the 2 rear wheels can independently turn. It's what's called an Ackerman steering system, so we can pirouette in place, for example. Solar powered, so there's no consumable on the rover. As long as we can get enough sunlight on the clean arrays to generate electricity, the rover will keep going. It has a deployable mast that supports several camera systems. One of the aspects of this mission and these vehicles is that they're visually rich. Up here are 4 cameras. The cameras are arranged in left-right stereo pairs. So there is a set of scientific cameras that have color filters, and then there's a set of wide-angle navigation cameras. And because there's a left-right pair, we take stereo images. The rover sees stereoptically. It has depth perception, and it uses that information to navigate as well as to return that information to Earth so we can get a 3-dimensional view of the planet. There's another set of cameras down low here in front. These have fisheye optics. They have about 150 to 180 degree field of view, so we'll see everything in front of the rover. And there's another pair in the back. So there are 8 cameras in 4 camera systems alone that you see here. And also notice that the cameras up here are very much at human height. So the images it takes have very much a human perspective. In addition to all these cameras, on the front of the rover there's a robotic arm. It's about the size of your own arm. It has 2 joints at the shoulder, 1 at the elbow, and then 2 at the wrist. And then there are 4 devices on the end of the arm. One of them is called the rock abrasion tool. This is it's like a little Dremel tool. This is the analog of the geologist's rock hammer, where a geologist likes to go out into the environment with their rock hammer, look around for interesting targets, crack open those rocks, and then look inside, because the exterior of the rocks have been altered and weathered. So the pristine material is inside the rock. So by grinding into it, we have access to that pristine material. I also mentioned, if you look carefully, there's a little aluminum shield on this. These rovers were designed, the project started in 2000, they were launched in 2003. Of course, we all know September 11th, 2001 was a tragic event here in this country. The developers of this rock abrasion tool went to the city of New York and requested 2 scrap pieces of aluminum. They reprocessed the aluminum from the World Trade Center, and they now support an American flag that's positioned on this rock abrasion tool, and that's now been operating on the surface of Mars. In addition to this device, there's also a microscopic imager, and it's the analog of the geologist's hand lens. So you crack open the rocks, you look at them in your magnifying glass, you look at the crystalline structure, the morphology, the shapes, the textures. We also have 2 contract spectrometers. This one here is an alpha particle X-ray spectrometer. Uses a small radioactive source to produce alpha particles that stimulate X-ray emissions in the surface chemistry. By looking at the characteristic X-rays, we can determine the elemental composition from about sodium on the periodic table up through about chromium on the periodic table. And then there is on the other side, there's a Mossbauer spectrometer, which allows us to differentiate the oxidation state of iron-bearing minerals. There's also a thermal emission spectrometer that's in the belly of the rover that looks up the white mass you saw in the previous frame. So taking together these spectrometers, these cameras, and the independence of this vehicle, we have effectively a robotic field geologist. And what we've been doing on Mars is classic field geology for now 8 years. So now we need to get this thing to Mars. Some people call this the Origami Rover. Others call this the Transformers without Megan Fox. The way this works is we fold the rover up. We need to fit it into a small package. So the mast stow, the solar rays fold up, the wheels tuck in, and it sits on top of this tetrahedron lander, which folds up. And you can see airbag systems on each of the four faces of this tetrahedron. We then put it inside a aeroshell with a leading edge heat shield, a supporting solar array and propulsion system to make this an interplanetary spacecraft that will travel from Earth to Mars. So this rover has to go through a metamorphosis. It starts off as an interplanetary spacecraft, it then has to go through an entry, descent, and landing on the surface, and then become a freely roving rover. So in 2003, we launched Spirit during the daytime in June, and then Opportunity at nighttime in July. And then they took a 6-month trip halfway around the solar system. And here is where the two rovers are going. They're going to two different spots on the surface. Spirit is targeted for this giant crater called Gusev. It's 100 miles in diameter, 160 kilometers. And you can see from this orbital image that it's the site of a great inflood. Here's a deep channel. You can see the ancient river delta here. You can even see where water breached out and flowed to the north. So the thought here is that this is evidence of where we would find sedimentary deposits based on the visual evidence. This red ellipse is our landing bullseye. And so not only do you want to go someplace scientifically interesting, but you want to go someplace safe. Because if you don't land safely, you don't get to do the science. So you want someplace that is large and flat. And so this provided an excellent opportunity to land safely, but to examine the possibility of sedimentary material. On the other side of the planet, almost 12 Martian time zones away, is this place called Meridiani. And this coloring that you see on this map is a mineral map for the mineral hematite. Hematite is an iron oxide that forms in water. So, and this is the only place on the surface where we see hematite. And so this is evidence, chemical evidence of water playing a role. So visual evidence of water, chemical evidence of water, two different hypotheses on both safe places to land. So Spirit landed on January 4th, 2004. Opportunity landed on January 25th, 2004. That was 8 years ago. And this is just a rendering of the sequence that we go from this interplanetary spacecraft to this entry, descent, and landing system. So we hit the atmosphere going at about 12,000 miles an hour. So even though you have a thin, tenuous atmosphere, at those speeds, you do get ablative heating of the heat shield, but all that friction does slow you down, and we go from about 12,000 miles an hour down to about Mach 1 in about 30 seconds. The heat shield gets to about somewhere between 2,000 and 3,000 Kelvin, but our rover is safe inside. It ejects the heat shield as it descends on a parachute. It drifts down in the parachute. A radar altimeter senses our approach to the ground. It then inflates those airbags you see, and it completely encloses the rover in these giant airbags. In this room, the airbags would inflate all the way to the ceiling, so a gigantic cocoon. And the tether that's holding the airbags to the parachute and back shell gets cut, and this gigantic beach ball with a $400 million rover hits and bounces down onto the ground and eventually comes to a rest. The airbags deflate, and then that four-sided pyramid is revealed. Now you're thinking, okay, some of you probably play Dungeons and Dragons, deal with different sided die, and you're thinking, okay, four-sided object, is a 1 in 4 chance this thing's going to land upright? Well, we play with a loaded dice. Actually, the center of gravity is offset. But even if this vehicle were to fall on its side, the way the lander opens, it opens like the petals of a flower, and it automatically rights itself. And so here is just a rendering of the sequence on the surface. So the lander would open up, revealing the rover inside. The first thing we do is to deploy the solar arrays to get power, because we've been on battery ever since we went through the landing sequence. We deploy the mast. And then on subsequent days, we'll stand up on the wheels. And the rover has been controlling everything. And so there's a massive umbilical that connects the rover to the lander. That gets cut, and then our rover drives off onto the surface of Mars. So here's the first color image taken by Spirit, and she is still on her lander at this point. You can see the airbags in the foreground. And now we had a vehicle that was designed for 90 days of operation on the surface. So the clock was ticking. we have a vehicle that has the ability to traverse about 1 kilometer, 6/10 of a mile. And so we saw all these rocks out here, and the scientists were excited because there weren't too many rocks to make it difficult to drive, but there were enough rocks to make it scientifically interesting. But we did stare at the distance, and right here, about a couple of kilometers away, are these hills that we thought, oh gosh, you know, won't it be exciting when future missions are able to explore Martian mountains? Well, here we are, driving off. So here's the lander. This is taken with our rear hazard avoidance cameras. So here you can see the remnants of the umbilical that we had to sever, the 2 rear wheels, driving off, the airbags neatly tucked up underneath. And we went right to work. And here the robotic arm extending out, grinding into this particular rock and measuring the chemistry. And we came up with our first surprise. We were looking for sedimentary material. This rock turned out to be volcanic. It's a piece of lava. And that was very surprising because we were looking for sedimentary rocks. Well, 21 days later, Opportunity lands at her site on the other side of the planet. And here's a shot of her landing system. And she lands at a small crater. This is about a 20-meter diameter crater we call Eagle Crater. And she hits a hole-in-one right out of the gate. Because see this is exposed rock? This is bedrock. This was an aha moment, because this is fundamental material that makes up the planet. And we drove up to it, and you can see the wheel tracks. No, that's not a boot print. That's a wheel track. And you can see where we ground into the rocks. But if you look carefully, you'll see the laminations in the rock. These are sedimentary rocks. These were laid down in water billions of years ago. And by measuring the chemistry in these rocks, we know that it was a briny environment, an aqueous, briny environment that was evaporating, because we see different concentrations of salts here versus here. So this was very exciting. This was confirming evidence that there was sustained liquid water on Mars. And the fact that it was liquid means that not only did you have to have a thicker atmosphere, you had to have warmer temperatures. You had to have a more Earth-like environment. Now, Spirit continued to explore. So if you look carefully, you can just, it's right here. You can barely make out the lander. You can see us driving. We stopped. We did some donuts in the mud. No, actually, we were using the wheels to break up the terrain to see what's just beneath the surface. But all these rocks turned out to be volcanic. So Mars had thrown us a curveball that we landed in what we thought was a sedimentary location, but it has since been obscured by volcanic activity. So we were able to drive by this crater we call Bonneville. So this is about 100 meters in diameter. This is a very old, highly eroded crater. But the thinking here was that this was an impact that broke through the surface and kicked up material, and perhaps we might find in some of the ejecta, some of the rocks beneath this obscuring basaltic layer, maybe we could find some sedimentary rocks, but we were unable to at this point. Switching sides again, back with Opportunity, she was able to drive over to this crater, which was only a few hundred meters away. We call this Endurance Crater, and this was a crater we thought we could drive down into. Now, these rovers were never designed to go up mountains or down into valleys or into craters. We wanted to go in here because craters are like time tunnels. It's a big hole in the ground that we know that the rocks down at the bottom are older than the rocks up at the top, just like when you go to the Grand Canyon. You know that the stuff down at the bottom is older than the stuff at the top. So it was like a time tunnel. So by going down in, we could go back in time. So what did we do? Well, we went to Home Depot. We bought a whole bunch of lumber, a whole bunch of those concrete paving stones, the kind that your spouse wants you to put out by the back door. We assembled it into this huge table. We glued the paving stones in. We had graduate students gluing pebbles onto this thing, covered it in sand, and then we had a large crane lift this thing up to make a variable tilt table. We took our engineering rover, and we wanted to make sure not only could we drive safely down these steep slopes, but we didn't want it to be a suicide mission. We wanted to make sure we could come back out again. And sure enough, it did have that capability, and we drove down in. Now, this is a false color image of inside Endurance Crater. It's false color. Mars does not have a blue sky. But you can see the wheel tracks as we go down, and you can see the variation in geology, each of these geological units. And these are like the chapters in the Martian history book, laid down in sequence. So this is what the geologists call an in-sequence stratigraphic section. And you can see all the places that we ground in and measured the chemistry going down. And what we found is that Mars has a rich ancient history that's episodic. It's changing. At one time, it was wet. We found evidence of minerals that form in water. Other times, it was dry. Not unlike Death Valley in California, where you'll have shallow lakes that persist for a season or two and then disappear for many years and then get covered by sand dunes and then reoccur again. So a dynamic ancient history on Mars. This is a picture of a crashed alien spacecraft. That's not meant to be a joke, because on Mars we're the aliens. This is our heat shield. This is what brought us safely to the surface. It did a belly flop here and broke into pieces. It's actually a really cool crash site, because the mechanical engineers were having a field day because they were looking at all the busted bolts and the sheared off springs and the like. But this gave us an opportunity not only to assess how well our engineering system did, because often it's a binary result. Either it works or it doesn't. This gave us an opportunity to see how well it worked, and it did work quite well. But also it gave us a chance to see what a recent impact might look like on the surface. But time is ticking at this point. It's a 90-day mission. We've actually run pretty close to being out of those 90 days, but the rovers are still going. And so we're able to drive. I mean, the great thing about a roving mission is that because you move, it's like every new day is something new. It's just like taking a vacation. You could take a vacation where you stay in the same resort the whole time, but if you get your boss calls you up and say, oh, take an extra week for your vacation, you get to go to a new spa or a new location. And that's what we're able to do. So Opportunity, by this point, has driven several kilometers, has exceeded its 90-day lifetime, and has exceeded our design distance, and it's still functioning. We came up to this highly eroded crater here. And when we looked at the rocks, we again found evidence of sedimentary material, but there's a difference here. See these laminations? They're not linear, they're wavy. This is evidence of ancient flowing water. This is a dynamic system. So this is an ancient shoreline or an ancient stream bed. So yet another piece of evidence that's enriching our understanding of ancient Mars and demonstrating or revealing that Mars was much more Earth-like about 3.5 to 4 billion years ago. And it was in that time frame that life started on Earth. So we know at this point there are at least two planetary systems, Earth and Mars, that had strong similarities. Life starts on one, so obviously the question is, did it start on the other? Of course, you always want to see where you came from when you take a trip. This little pale blue dot is the Earth seen just before sunrise by the color cameras on the rover. And this is essentially 20/20 vision, so this is how it would look to an astronaut, illustrating how far these rovers have actually traveled. But they're continuing to travel. Spirit has driven across Gusev Crater a couple of kilometers and has reached those hills I pointed out in that first color image. So we far exceeded not only our lifetime, but our distance requirement, and we're starting to climb the hills. Our hypothesis is the hills are much older material, and so may contain evidence that predated that volcanic era that has obscured the sedimentary material. And it's here on the Columbia Hills, as we climb up, that we found our first evidence of water-altered rocks. So these rocks, here's characteristic laminations, characteristic alteration of minerals on the surface. So this is Spirit's aha moment, finding evidence of liquid water at this particular site. This is a series of images snapped that gives us our visual clue as to why the rovers have been able to last so long. They were designed for 90 days. That was the requirement from NASA. One of the limits on the rover's lifetime was dust accumulating in the solar rays. So we sized the solar rays to be big enough to handle what we thought was the worst case dust accumulation, and we could achieve our 90-day mission at that point. But we get these wind gusts that you see manifested here as these dust devils that will blow the dust off the arrays and give the rovers a new lease on life. And this has allowed our extended mission. Now, some of these are quite large. Even though Mars has a tenuous atmosphere, we do have high winds. Some of these are many tens of kilometers in diameter. You can imagine Dorothy and Toto being sucked up in this one here, for example. So we were able to climb the Columbia Hills. And one of the outcrops that we studied here turned out to have a high concentration of carbonates. Now, carbonates is one of the minerals that scientists have been looking for on Mars for years. The reason is that one of the theories as to what happened to the atmosphere on Mars is that it is now sequestered in minerals that make up the surface rocks. Just like here on Earth, carbonates here are found in the Earth. are remnant of the ancient carbon dioxide atmosphere that we had on this planet. This outcrop turns out to be about 30 to 40% weight calcium carbonate. And so this is reinforcing our understanding of the ancient planet. Further, because of the presence of carbonates, mean that there had to have been liquid water to allow these minerals to form. And carbonates form in a neutral pH environment, which is the kind of environment that we think life started in. So at this point, here with this image, after crossing the Columbia Hills, Spirit has been operating for over 2 years on the surface. So, more than 8 times its lifetime, and here's where we had the first serious mechanical failure of the vehicle. You can see the pair of Rover wheel tracks driving along here, but as you look down here, you'll see now there's a difference between the 2 wheel tracks. It was here that the right front wheel of the Rover failed and stopped spinning. Now, the Rovers have small motors that have very large gearboxes, a 1,500 to 1 gear reduction. So when a wheel motor fails, you can't back drive the wheel. You have to drag it. It's like one of those annoying grocery store carts where the wheel is jammed and you're trying to push it down the aisleway. So we can drive the Rover backwards with the remaining 5 wheels, dragging that 1 wheel. It means we have to apply more shear force to the surface in order to move it, because it's like a ball and chain. But it turns out to be a scientific bonanza, because that wheel scrapes the surface, revealing just what is beneath it. And this here is identified as a magnesium sulfate, like Epsom salts. It's a hydrated magnesium sulfate that's unconsolidated. So it's evidence of perhaps more recent water action on the planet Mars. Opportunity continues to drive like crazy. We've covered kilometers, and we keep finding signatures of water. So, the water that was on the surface of Mars at one time wasn't just a puddle or pond, but perhaps kilometer-scale bodies of water. And this is another crater that we approached called Victoria Crater. This is a half-mile in diameter. Bigger crater is a deeper crater. A deeper crater means you can go further back in time by going down inside, and we wanted to go down inside this crater. Now, at this point, we've actually been on Mars for several years, and the next Martian mission has arrived at the planet, the Mars Reconnaissance Orbiter, an orbiter that has a high-resolution camera, and it has taken a picture of Victoria Crater. But if you look carefully, you can see the rover wheel tracks as we are driving and exploring around. And if you look at this little dot there, that's opportunity down on the surface of Mars. This greatly enhances our ability to explore, because these are like our eyes in the sky, can see small-scale objects that can guide opportunity for further exploration. And this becomes a powerful research tool for us. Now, we've been on Mars so long that we encounter what I was telling my colleagues earlier today, the equivalent of Y2K. Remember when everyone thought in the year 2000 that all this computer software that allocated only 2 digits for the year would come crashing? Well, when we designed these missions, they were designed for 90 days. We thought, well, maybe for luck we'll get 120, 180 days out of it. So we allocated only 3 digits for the Martian day number, what we call a SOL. We are at now SOL 999. Our flight software and our ground software is going to break at that point. So we had to do a major software upgrade on the rovers. And we did that, and while we were at it, we added new capabilities to the rover, new autonomy. And that's what's illustrated in this picture here. Here you can see the rover wheel tracks. Here you can see a hazard. What we deliberately did is we told the rover, I want you to drive to a target over here. The rover was positioned back here. So normally the rover would drive in a straight line. The rover was using autonomous navigation, meaning that it uses its camera system to assess the terrain in front of it. And it properly recognized this as a hazard. You can see where it paused here, imaged that and said, I'm not going to do that. But then it problem solved. It figures, okay, how do I achieve my target, my goal? And so it says, okay, I can plot a safe route this way, and the rover, in fact, did that. And so that's part of the autonomy that these rovers have. Because contrary to popular belief, I do not have a team of teenagers back at JPL with game consoles driving the rover, because radio signals take too long to get from Earth to Mars. The time delay is anywhere from 5 minutes to 21 minutes, and then the round trip time. The way we operate these rovers is that they sleep during the night, preserving energy. They wake up with the sun. We give them their instructions for the day, and they autonomously carry out those instructions. And the most important thing is to always keep yourself safe. And that's part of the autonomy that we have on board these vehicles. So this is an augmentation that greatly allows us to expand the ability to explore. Now, at this point, we've been on Mars for about 4 years. And one of the hazards of exploring Mars are great Martian dust storms. But they happen only about every 2 Martian years, about every 4 years. 90-day mission, we were landing in the summertime, which is a storm-free season. It's not a worry. But now we're 4 years on Mars, we get into that storm season, and we experience a global Martian dust storm. And this illustrates the successive, this is typical noontime on Mars, about 11:14 in the morning on Mars, and how dark the skies became over subsequent days. These are solar power rovers. They need sunlight to stay alive. The important thing is they need the solar energy to keep heaters operating inside the vehicle to keep it warm, because the temperatures get down to minus 140 degrees Celsius at night on the rover. And so the rovers would freeze if they were not kept warm. And so our concern was that the vehicle would be starved for power. They were never designed for this kind of environment. But we were able to hunker down. We turned off all unnecessary systems. We operated the rovers just enough to put enough waste heat into the vehicle, kind of like putting on your parka and then jumping around in the cold. You know, just like they tell you if your car gets stuck in the snow somewhere, is that you don't keep your engine running. You turn it off for about an hour, and then you turn it on for about 5 or 10 minutes to warm the car up again, and then you turn it off again so you don't run out of gas. Same kind of thing we did on Mars with this vehicle. But the skies did clear, and they cleared for both rovers. And so we continued to explore. This is another picture with Spirit, and again you can see the effect of the wheel we're dragging. But here we had perhaps one of the most exciting discoveries of the mission to date. This light-colored material, this very white material, is amorphous silica, revealed by that broken wheel dragging through the soil. Amorphous silica is a precipitate from a hydrothermal system. So not only do we have liquid water, but we also have an energy source. This is a big deal, because here on Earth, wherever we have hydrothermal systems, we have teeming ecosystems. Think of the geysers of Yellowstone. They're teeming with life, or deep ocean volcanic vents. So here we have evidence of an ancient environment on Mars, which there was liquid water, warmer temperatures, and an energy source. You know, the essential elements, physical elements, that provide a habitat that could have supported life. But these rovers are challenged by the environment, and one of them, as I mentioned, is dust. This is a self-portrait. This is Spirit updating her Facebook page, you know, just like you take your cell phone out and you take your own picture. The rover uses the cameras up in the mast to take a mosaic, and this is a mosaic of several hundred frames. And you can see the dust on the arrays that were almost completely camouflaged against the environment. And this is what is limiting the life of the rover. Now, we get some cleaning events every once in a while, but there's a systemic or secular increase in dust that constantly decreases the energy. It may pop up every once in a while when we get a dust cleaning event, but dust continues to accumulate. And so what we've had to do for Spirit for subsequent winters is actually literally park the rover on an incline, tilting its solar rays towards the sun where it will be in the wintertime to maximize the solar insolation, maximize energy production. At the end of the 3rd winter on Mars, we had to tilt the rover 30 degrees. Problem is, with its broken wheel, we can't tilt this rover more than that. We can't find a slope steep enough that we could actually drive up to get that tilt. The 30-degree tilt we actually got by driving down onto something. So we were hard-pressed to decide what we would do for the coming 4th winter. And so we were driving to try to do some science in which Spirit fell into a camouflage tiger trap. This turned out to be an ancient small crater that was filled in with loose fine material covered with a camouflage dirt crust. And because we dragged that one wheel, the other wheels have to apply more shear force, and it broke through that dirt crust, and the rover collapsed into this loose fine material. You know, any of you that's gone snowshoeing and you're on hard-packed snow every once in a while, you'll hit a place where you break through the crust and you go sinking down in, and then there's no cohesion, no bearing strength to that, and you try to lift up and you try to step again and you break through again because you're applying more force to try to lift yourself. Same kind of situation. You can see how buried this one wheel is. The other wheels were buried as well. Additionally, the rover was sinking into the ground as a result of us trying to spin the wheels. Here we're using the microscopic imager the digital hand lens on the end of the robotic arm in a way that was never intended to actually photograph underneath the rover. So you can see here one set of wheels, here the other set of wheels. We're tilted, it's a sloped terrain, and we even have this large rock that's about to high center the bottom of the rover. This is a very dire situation for Spirit, because with only now 5 operating wheels, and we're now embedded in loose material, and we have no traction. Just like, all of you, I'm sure you've had your car spinning wheels on hard ice, that you just get nothing out of it. But out of every demise that Spirit has experienced, it always resulted in a great scientific discovery. This is the loose fine material that gets churned up by the rover in this tiger trap. And this is a highly rich environment of different mineral types that are all unconsolidated. These, again, are sulfates, calcium sulfate, iron, manganese sulfate, but they're unconsolidated. What made this trap so hazardous is that sometime in the recent past, maybe 1 million years ago, when there was a different obliquity of the planet, where the axis was tilted differently, there was likely snowpack in this area. And we had an effect what's called solid-state greenhouse effect, where sunlight could penetrate through the snow and melt the water underneath. But because it was embargoed underneath that ice, it could be liquid even at low atmospheric pressure. And it could flow, dissolving minerals that pooled into this small crater, and eventually over time filling it up with these unconsolidated minerals, such that 1 million years later our disabled rover comes driving along and collapses into it. So it's scientifically exciting, but it ended up being the last resting place for Spirit. And we tried valiantly to try to extricate the rover. And you can see here driving, you see how completely buried this one wheel is and what an anchor this particular wheel is. And we were actually making progress at extricating the rover until we ran out of time. Winter came upon us and we lost the ability to generate energy. And because we couldn't tilt or position the rover favorably, the rover went silent during the winter. In other words, it didn't have enough energy each day to maintain communication. We had hope and expectation that the rover could survive the winter and wake up again in the spring, but it never did. This is sunset on Mars, taken by Spirit. On Mars, the sunsets are backwards. Here on Earth, we have blue skies and pink sunsets. On Mars, you have a pink sky and blue sunsets. And you notice that the sun actually looks quite small on the horizon because Mars is about 50% further from the sun. So we had to say goodbye to Spirit after 6 years, a very successful operation. But opportunity is still going. This is Victoria Crater. We spent over a year inside it exploring, and we decided we want another adventure. So at this point, we've traveled about 13 kilometers. So this is a map. This is where we landed with opportunity. This is Endurance Crater, that first crater we went down in. This is the over 6 kilometers we drove to get to Victoria Crater, and here's where we are. So this distance here, you can see a scale here. So keep that distance in mind, because what Opportunity has since done is here's Endurance Crater, here's Victoria Crater, here's the distance we drove then. But since that time, in the remaining 3 years, we've driven this distance over here to Endeavour Crater. This is a 22-kilometer diameter crater. We had to more than double the odometry on the rover to get here. We never thought, we weren't sure whether the rover would ever make it. I mean, this is, you figure you buy a new car, it's rated for 100,000 miles. Our rover was rated for about 1 kilometer. We did 13 kilometers, so we did the equivalent of, 1,300,000 miles on your car. And now we had the guts to say to NASA, oh, we're going to double that odometry and go and reach here. And in fact, the rover has survived to do that. We have now about 30.3 kilometers of odometry on Opportunity. Why did we want to go to this crater? Not because it was bigger, but because from orbit, we see in the rim of this crater, this ancient rim, because you can see it's a very old, highly eroded crater. This is reveals material from an earlier epoch on Mars. We've been pretty much exploring what's called the Hesperian era, sort of Middle Age period on Mars. We want to go to what's called the Noachian era, which is ancient Mars, the time in which Mars was wet. And so this is, we believe, Noachian material. So this is from the earliest period of Mars. And from orbit, they see evidence of clay minerals in the rim of this crater. And clay minerals are particularly interesting because not only do clays form because of the action of water, but they typically form in neutral pH water, which is further of interest to the astrobiologists. And then clay minerals have a tendency to preserve or to entomb whatever was in that water when they form. So clay minerals are excellent places to look for ancient samples of what existed at the time the minerals formed. So we want to explore those clay minerals. And so here we are. We've pulled up to the rim. You can see this giant rim that looks like a mountain range. And we know that there are clay minerals up here that we are going to approach. Right now we're heading into a winter for opportunity, and we had to take some action of actually parking the rover again to get favorable solar illumination. So the rover is stationary right now, although scientifically active. Once we pass the winter, we intend to drive down here and to explore the clay minerals that we see up in these reaches here. But in the site where we are right now, we found exciting evidence. This linear feature of material, this vein, is gypsum, calcium sulfate, a hydrated calcium sulfate. This is probably the best evidence so far of ancient liquid water on Mars, because this had to form in place, because this is a fracture in the rock. The water percolated up, precipitated out the gypsum, which is one of the more insoluble minerals. So we know that there was water at this spot on Mars back some 3.5 to 4 billion years ago. Now, even though the rover is stationary right now, we're doing a very important scientific experiment, which is we're tracking the radio signal for the rover. And by measuring the Doppler shift in the radio frequency, we can measure the relative motion of the rover. And you might be saying, well, the rover's not moving. But it's fixed to the surface of Mars, and so it becomes a proxy for the rotation of the planet. And so we're measuring the spin axis and the angular momentum of Mars very precisely. And the reason for doing that is by knowing the moment of inertia for the planet, we get a handle of the mass distribution inside the planet. So maybe we can get a handle on the size of the core on Mars, which is still a yet to be determined quantity. Further, we're doing an experiment that probably many of you have done in your own kitchen. If you take a chicken egg and you spin it, you can tell whether it's raw or hard boiled, right? Because if it's hard boiled, it freely spins. If it's a raw egg, it sloshes and rolls to a stop. Well, planets do the same thing. So by measuring the nutation in the planet, the slosh, the wiggle of the spin axis, we can determine whether the core of Mars is liquid or solid, yet another unknown aspect of the planet. So there's still a huge amount of exciting science that Opportunity can still do, and the rover is still in relatively good health. But shortly, Opportunity will not be alone. The next rover, Curiosity, the Mars Science Laboratory, is on its way to Mars, and this is a much bigger rover. This is a bigger rover, can traverse more difficult obstacles, and can carry a lot more instrumentation. You can get a size of it. It's about the size of a Mini Cooper. It's 5 times the mass of Opportunity, and it carries over 10 times the amount of instrumentation. One of the very exciting instruments is called the Sample Analysis at Mars instrument, or SAM. It will take advantage of having a very large robotic arm that has a drill that can extract core samples from rocks or soil, pulverize that, and introduce those pulverized samples into the SAM instrument, which has a mass spectrometer. And so it can do it not only an elemental analysis, it can look for complex organic molecules. We know from examining meteorites that there are organics, amino acids, nucleic bases that have been found out in the solar system. The question is there an inventory of organic material on Mars? There have been recently detected trace amounts of methane in the atmosphere of Mars, but are there more complex organics? Are there the building blocks for life? Because Opportunity and Spirit have firmly established that Mars had a habitable environment. There was liquid water, there was warm temperatures, there were energy sources, the water was dynamic, neutral pH, so you had an environment that was very much like the Earth. Now, were there organic compounds? And so the Mars Science Laboratory might be able to answer those questions. Now, it is too massive to land on Mars using airbags like Spirit and Opportunity. It instead will use a rover jetpack, what's called the Sky Crate. Here's the main chassis of the rover underneath. This jetpack with the propulsion tanks fits over the top of it. Here are the large rocket engines, and this will actively fly the rover near the surface and then lower the rover down on a crane to touch down on the surface, and then the jetpack will fly away and crash. And then the rover will drive off on the surface. It lands on August 5th, so mark your calendar and follow along with that. So we will have 3 generations of rover technology on Mars. These are all our engineering test units at JPL. This one we've nicknamed Madame Curie. This is a fully functioning rover, just like the Sojourner rover. This is my surface system test bed. This is the twin for Spirit and Opportunity. And this is the vehicle system test bed, the twin for Curiosity on Mars. You can get an idea of the progression in size. This rover is about 10 times the mass of this rover. This rover is about 5 times the mass of that one, so they keep getting bigger and better. And all of this is to look at the question as to whether was Mars the Earth's twin at one time? Are we alone? Is life unique to the Earth, or is it found elsewhere out in the solar system? And importantly, Mars changed radically from the Earth. If it was at one time Earth-like, why did it change? What happened to it? You know, we know so very little about planetary evolution, and we're facing important issues like climate change and global warming. So understanding how planets evolve over time is essential to making intelligent decisions so we can be good stewards of this planet, our home. So I hope you'll continue to follow along. Everything I've shown you today can be found on the JPL website. The images appear there just as quickly as they show up for my operations team, so you can follow along in the adventure that's ongoing. And I thank you very much for listening. Thank you. Thank you. Thank you. I imagine, Eric, we have a few minutes for some questions, so I'd be glad to take, yes, this gentleman right here.
What is the power source on Curiosity?
Curiosity will be nuclear powered. This spec here, it's not installed, will hold a radioisotope thermoelectric generator. It uses plutonium-238, which is not the weapons-grade plutonium. It has an 86-year half-life, and so naturally decays producing heat. You use thermocouples to convert that into electricity with about a 4% conversion efficiency. No moving parts, and you get energy, you know, that decays, you know, with a half-life of 86 years. Other questions? Yes? Well, you know, I grew up when Neil Armstrong walked on the moon, and everybody knows the name Neil Armstrong as the first person to set foot on Mars. But no one remembers Surveyor, which was the first active lander on the surface of the moon. You know, our robotic vehicles have been very successful at exploring, and they exhibit many human-like qualities in their exploration. They're very good at what they do. And the great thing is you don't have to feed them, you don't have to pay them, and you don't have to bring them home. But there is a certain intangible of sending humans. So it's likely that we will continue the robotic exploration of Mars, but we talk about eventually sending humans there at some point. I can't say when that is, but our robotic vehicles keep getting better and better. A question down here, yes?
I've seen a simulation of the deployment and landing of Curiosity. And, you know, the first thing I thought when I saw that there must be a simpler way. I mean, there's a million ways for something to fail. But how did it get to that point?
Yeah, the question is who came up with that idea to get down to the surface?
Yeah.
You know, the challenge for Mars is that you have to get rid of all the kinetic energy you put into your rocket to get you into space, to get you on your way to Mars. I mean, you arrive at Mars, you know, traveling, you know, kilometers per second, and a huge amount of kinetic energy. And because Mars has such a thin, tenuous atmosphere, you can't rely on the atmosphere to get rid of all that energy for you. So you have to use these other systems of an aeroshell, and then a parachute. And then you want to be able to target the location where you want to touch down. And so you end up coming up with these complex systems that have to work perfectly. In the case of the Spirit and Opportunity, there was over 150 individual independent systems that had to work perfectly in order for you to safely land. And so it is a very risky and dangerous undertaking. But right now, technically, it's the only way we have been able to develop to get down to the surface and to get down to where we need to be. Just coming here.
Where is Curiosity's landing site going to be?
It's going to be nowhere near these other two rovers. It's a place called Gale Crater. And because we can more precisely target the landing site for Curiosity, its landing site uncertainty is about 10 kilometers, where for Spirit and Opportunity it was about 100 kilometers. We then have we can go to many more places because we can find smaller, safer places to land. Gale Crater is of interest because they see the evidence of clay minerals, although I hope Opportunity will beat her to clay minerals. But there's also many, many different stratigraphic units that extend over kilometers. So the thinking is that Curiosity will have the opportunity to explore a huge range of Martian history when it arrives. Yes, back there, yeah.
What were some of the design changes made to Curiosity due to the problems you encountered in this mission? I guess you made it nuclear as opposed to solar.
Yeah, that's the big difference is we went to a nuclear power system to avoid the time limitations that solar rays. Now, people often say, well, gee, why didn't you put windshield wipers or compressed gas or something to blow the dust off the solar rays? And you have to remember, we were originally only meant to be a 90-day mission. So for longer duration rovers, we are considering active mitigation systems. But you have to be careful. Those always add complexity, they add mass, and they add cost. And so, sometimes it's just easier to do the simple thing, which is just make the solar rays bigger. So, so solar rays versus RTGs was one of the changes that Curiosity has. Another one is it has more redundancy. There's very little redundancy in these rovers. They're all single string. One part breaks, it's over. So Curiosity has redundant power systems, redundant computers, redundant control systems, and it also has brushless motors where Spirit and Opportunity have brush motors. So the thinking is the mechanical systems will have greater longevity. Yes, over here.
Have you guys ever considered using ASRGs instead of RTGs, or maybe waiting till the ASRGs were more foolproof?
I'm sorry, SRGs, the Stirling cycle. The technology is just not mature enough. They do look at, they are developing active generation systems that have greater efficiency, but they're not mature enough to be able to fly to Mars yet. Way in the back there, yes.
You mentioned that when you're going down to the craters, you can see the changes in stratification between like wet and dry climate almost, and then finding the volcanic activity. Was the crater record going down to them give you a detailed enough history to see when those started to stop happening on the planet?
No, I mean, in geology, it's very difficult to absolute date geologic rocks or units. The best you could do is relative. The best you can say is this is older than that. What you need to do is to do isotopic analysis, which right now would require terrestrial-based investigation. What we hope to do is the next mission after Curiosity, which may be a decade away, would be a sample return mission to actually bring back carefully selected samples such that we can analyze them in the laboratory. We can throw the full analytical instrumentation that exists here on the surface of the Earth at it, looking at these things. And one of them is to do absolute dating of the rocks. How about two more questions, and we'll wrap up here, because I don't want to keep you from things. Yes?
For Curiosity, what's the anticipated mission length on the surface?
Well, the problem is Spirit and Opportunity have raised the bar so high that everyone is reluctant to give a date, because you either have to greatly exceed it, because people will say, well, why can't you do a factor of 10 better than Spirit and Curiosity and Spirit and Opportunity? And so the design right now is actually just one Martian year, which is approximately 2 Earth years. The expectation is the rover would survive longer than that, but that's the design point for the system, where the design point for Spirit and Opportunity was only 90 days. And one last question. Yeah, go ahead.
I was wondering, on Curiosity, will you be able to first wheel the wheels, or do you still have to drag?
The Curiosity does have a different drive actuator design. It does have a clutch system. So if we do have a failed actuator, you can disconnect the drive system, and so it will freewheel. It's important to remember, the reason why Spirit and Opportunity had the design they did is when you turn off the power of the motors, it parks itself. It's so if you drive up onto a slope, you don't want to turn off the power and then all of a sudden, I mean, it's just like, forgetting to put the parking brake on in your car when you on a steep slope. So Curiosity has a more complex system, which of course makes it more susceptible to problems going down. So it's always this trade of complexity versus simplicity. Well, thank you very much. I enjoyed having the opportunity to speak with you today. Thank you.